Hi everyone, this is a short video going over the practice quiz, and hopefully this will get you in good shape for today's quiz. I wanted to make sure you got some feedback before you dived in. So, starting with the first question, um, we have a wrench and it's being used to loosen a wheel nut. So you got this right, well done. It's simply the torque is equal to the lever arm distance. I'll just call that X multiplied by the force. And in this case, the lever arm distance was 0.5, and I'm going to include the units. That's very important. 0.5 meters times a force of 200 newtons. So if I put those units in there, that helps me get the units right on the answer, which is required to get your full credit. So we've got a half of 200, which is 100, and it's going to be Newton meters. Okay, so the only kind of key point there is don't forget the units. Then it says part B, one of the nuts is stuck and it won't move. You can't push any harder, you're applying the maximum force. What can you do? Some of you had some great creative ideas. The answer we're looking for physics-wise is we need to increase this lever arm distance, this X. So we could use a longer wrench, or we could slide a pipe over the handle if it would fit, that was longer. So for B, we want to increase the lever arm distance. Then with the same force, we can apply larger torque. So by increasing X, sometimes they use D to represent the lever arm distance, we will increase the torque proportionally. Okay, cool. Got to erase all this. How do I get rid of everything? There we go, clear. So question 2. This was talking about objects, whether they're stable or full when they're kind of tilting. So it said, why does this object fall over? So here's the center of gravity, and what we can see here is that this weight here, which acts in line with the center of gravity, is outside the base of the object. So here's the base here, and the force is outside. So that creates a torque turning it, with like the fulcrum being the corner of the block there. So if the center of gravity, let me just undo that, sorry, the center of gravity lies outside the base. So it will fall. It's unstable. The other example, it was inside, like here, it's inside the base here. So this force will make it rotate back towards being stable. So that's why that one's stable. Okay, question 3. Newton's law of gravitation, Newton's universal law of gravitation. So this one, some of you emailed me, this was a bit harder to wrap your heads around. F equals G m1 m2 all over r squared. Let's just take a minute to make sure that we know what all these terms mean. So G is the universal universal gravitational constant. It's constant. It never changes. It's just a number. That's all it is. So we don't really have to worry about that in these questions where we're just changing the mass or changing the distance. So we can just kind of set that aside for now. M1 is the mass of object 1. So we always have two objects to have a gravitational force between them. Both of them must have mass. So M1 is the mass of object 1. M2 is the mass of object 2. Remember, mass is measured in kilograms. Sorry for the poor writing there. And then R is the distance between them. between the objects. And that one is squared. So if we were using the formula, doing a calculation, and we gave you some numbers in your calculator, you'd have to square that number. Okay, so let's keep that up here. So those subscripts for M1, M2, they just remind us which objects they are. So we could have any two objects. Here's two planets, M1, M2, and they're separated to their centers. I've drawn it to the edge. Let's do that more accurately. To their centers of gravity by r. They're not separated by r squared, they're separated by r. But in the calculation, we would use r squared. So I don't know, let's just say, for example, because using planets, stars, large objects where we usually think about gravity, we have huge numbers. It's really confusing or tricky to talk about. Let's just say we had two rocks in space, two space rocks in some kind of asteroid belt somewhere. And let's just say they were both 10 kilograms, just to make things easy. And let's say they were 2 meters apart. What would be the gravitational force attracting them to each other? Eventually they're going to collide, I guess. So if we wanted to actually calculate that, we'd need to use g, and g is a really tricky number. It's a very small number. It's 10 to the negative 20 something. Not easy for us to do quickly in a quiz or a test. That's fine. Let's do it conceptually. The force is going to be g proportional, like multiplied by the 10 kilograms, and then the other 10 kilograms, and then we take that distance, 2 meters, and we'd square it. So we'd get 100 over 4 times whatever g is. And that would actually calculate it. Now we want to concentrate on what changes we would make to these rocks, and how that would change the force, how that would affect the force. So let's try that. So here's our rocks. Now if we double just one of the masses, so now this is 10 kilograms, but this one's now 20 kilograms. But we keep the distance the same. Let's say we keep them 2 meters apart. How would that force attracting those two rocks compare with our previous example? So we've doubled one of the masses. Doubled mass 2. So then we would get whatever we got before. We still got g, we still got 10 for our M1, but now we've got 20 for our M2, and our distance is the same, so it's still all divided by 4. So what's changed? Well, now we'd get g times 400 over 4. Here we go. Sorry, 200 over 4. That's twice as big as before. Last time we had 100 divided by 4. So by doubling one of the masses, M2, we've doubled the force. Well, now let's see what happens when we double both. If we double both, now if they're both 20 kilograms, compared to the first case when they were both 10 kilograms, and if the separation is still 2 meters, now we're going to have g, our constant, times 20 times 20 all over 2 squared. So now compared to before, it's 4 times as big because we've doubled both of them, and both the m's are in the equation at the top. Okay, so far so good. Obviously, if we halved one of the masses, just one of them, the force would halve. If we halve both, it would divide everything by 4, decrease everything by 4 times. So far so good. Now the separation is a little bit more tricky. So let's go back to 10 kilogram masses, keep everything simple to start with. What if our separation doubled? So now we say it's 4 meters. What's that going to do to our force? Well, remember initially we said that put our squared in there. We said that initially, if we just recap, we had G, our force was G times 10 times 10. So 100 over, initially it was 2 meters. So 2 squared. This is what we had before, but now it's 4. So how's that going to change? Well, if I write this up here in this corner, our force previously was going to be G times 100 over 4. But now we've said we're using 4 meters, not 2. So we've got to change this. This now becomes 4 squared. We've doubled this distance from 2 to 4. How does that affect our overall force? Well, keeping the masses the same, we've still got 100 G, the 10 times 10. Now it's divided by 4 squared, which is 16. So if we look, 100 divided by 4, 100 divided by 16, what's the change? That's a quarter as much. So if we double the distance, we decrease the force by 4 times. And we could use any numbers we wanted. We could, we use 2s and 4s because they're easy to deal with. But the key point is if you double the distance, the force is going to decrease times 4 because we're changing this. If I go to a new screen, because we're changing this R by 2. So if that's 2 times bigger, the change is going to be 2 squared. And because it's underneath the fraction, that's going to end up dividing everything by 4. So it's a quarter as big. What if we triple the distance? What if we make the distance between the rocks 3 times bigger? So now if we say, okay, well this R, it was 2 meters originally, now it's 6. So we've tripled it. It doesn't matter what the numbers are. If we've tripled it, then the change is going to be the same as saying, well, this is now 3 times R. So if we have to square that, we're going to get 9R. So whatever it was, it's going to be times 9 compared to whatever it was before. So tripling it is going to make it 9 times smaller, because this whole value here is going to end up 9 times a factor of 9 bigger than it was initially. Okay, hopefully that's cleared something up and not made it more confusing. It is a little bit tricky, but if you follow the kind of the pattern is to look at the equation. If any of these terms on the top double, it's directly proportional. So that's going to make F double. If it halves, it's going to make F half. If they both half, this is going to go down, the force will go down by 4. If we double R, because we just got to remember that it's squared, it's inversely proportional to the square. That means that increasing R, doubling it, is going to reduce F by 4 because it's going to be 2 squared. Tripling R is going to decrease the total force by 9 because we're going to end up with everything divided by 9. What if we halved the distance and made it closer? Let's think about that. Well, that would be the same as squaring a half, which is a half times a half is a quarter. Oops, sorry. So that's going to make the overall force, if we decrease the distance, if we decrease it by a half, that's going to make it divide by a quarter. That's the same as multiplying everything by 4. What if we made it 3 times closer, decreased it by 3, that would be then 9 times larger force. All right, moving on. We've got question 4, which is the pressure at 20 meters depth. So we've got pressure times weight density. I'll call that WD times the depth. So we've got 10,000 newtons per meter cubed. That's the weight density, which is just the regular density times the force of gravity, times the depth. Now for water, that's always the same, and that's given in the question, so we don't need to worry too much about that. We just do, we end up with 200,000. And what are our units going to be? Well, one of these meters is going to cancel with that one of those meters, so we end up with newtons per meter squared, which makes sense because it's a force over an area. That's what pressure is. Okay, what will happen if to the pressure at double the depth? So if we look at the equation again, just analyzing the equation, if we double the depth, then that's going to double P. So we would end up with twice as much, 400,000 newtons per meter squared. Okay, now question 5. We've got a rock. Why does it have a buoyant force? Well, these little arrows represent the forces, and they get more as we get deeper. So the arrows, as we get lower down, are bigger. The side ones cancel. This on the left side here is equivalent to this on the right side. This one a little bit deeper, a little bit bigger, is equivalent to the one on this side. They cancel each other out. But the top and the bottom don't. You can see this is a smaller arrow than this one. So overall there's upward force there and here. So the key is that the bottom of the rock is deeper, so there's greater pressure. They don't cancel out, so that creates the buoyant force. 5b, we've got these beaker, and we've got a rock here outside of it. Measure the mass, sorry, not the mass, the weight, and then we put it in the beaker, submerged, immersed. It says that the scale reads 20 newtons here when it's just in air, and then 14 newtons when it's immersed, completely submerged in the water. So what's the buoyant force? Well, it's just the force pushing up on the rock from the displaced water, the effect of the displaced water, and so it's going to be 6 newtons up in this case. So basically we've got to add up to that 20 newtons. So the 20 minus the 14 is equal to 6 newtons. That's the buoyant force. Okay, good. And then a bit more of another practical example, but sort of real life one, is this Falkirk wheel. Now this is kind of a crazy concept, but you know, it doesn't matter what size boat we've put in these gondolas. They've got to be balanced. There's 2 of them. Imagine them on a kind of like teeter-totter. It's kind of what it is. It's kind of rotates, but it's just like a teeter-totter. It goes all the way up, all the way horizontal, vertically, all the way around. But it's easier to think of it like this. Now, if we had this on a balance point, on a fulcrum, we know that if they're empty, they balance. Well, the key here is that the water goes all the way to the very, very top of these gondolas. So let's draw that a bit more precisely. It goes way, way to the top. Now we know that if we submerge if we put a floating object in there, here's a boat, in this side, that's going to push some of the water out. How much water is displaced? Well, it's equal, the weight of the water is displaced is equal to the weight of the boat. That's Archimedes' principle. That's what he figured out, that if something's floating, it will push out an amount of water equal to its own weight, but only if, you know, if it's like really, really, really full like that, which it is. So it doesn't matter how heavy the boat is. There could be no boat. In this case, they're always balanced, because this one has still got all its water. It didn't lose a boat's weight of water. If we put a huge boat in it that pushes out like almost all of the water, still floating. Most of the water's pushed out. How much is pushed out? Equal to the weight of the boat. So that in this case, we've got the force of boat 1. In this case, sorry, we've got the force of boat 2, the weight. It's much bigger, but it's pushed out lots and lots of water. How much water? Equal to the weight of the boat. So basically, when you add the weight of it all together, the weight of the gondola doesn't change. That's the structure. But the water plus the boat, like this whole thing is always the same. We'll call it a constant. Because if we put a heavier boat in, it just pushes out an equal amount of water, decreases the water by the same amount that we've increased the weight by putting the boat in the gondola. So it's always, always, always constant. Okay. So then it asked, this is the final bit, part B. What's the weight of water displaced from the gondola on the left? So we had a large boat here, some kind of ship. And it said the boat had a weight. And remember, weight is always in newtons. It's a force. Weight is not in kilograms. Mass is in kilograms. So mass is in kilograms. But if we want to get weight, we have to times it by the force of gravity, which we usually approximate to 10 newtons per kilogram. So this would have been a 2,000 kilogram boat. Don't need to know that for the answer, but I could see that some people are still confused about mass and weight. So that would be 2,000 times 10 newtons per kilogram. We get 20,000 newtons. So the question was, what's the weight of water displaced from the gondola? Well, let's remember this is full up to the top. I should draw that more accurately. So it's a 20,000 Newton floating object. It must have displaced 20,000 newtons of water. Because that's what we just learned in that previous question. Okay, I hope that helps. Reach out to me with any final questions before the quiz. We will have time. We'll probably push the start time of the quiz back to like 11:15, because I want to have a chance for you to email questions on or ask on the forum. Okay, best of luck to you all. Miss you guys, and talk to you soon.